Today we're going to start our first chapter in Weld 2510. And we're going to cover Chapter 1 out of our textbook, Pipe Welding Procedures. And Chapter 1 is simply an introduction. You know, what is pipe welding all about? What are the things you have to watch for on that? What are some of the basic techniques in generality? And we're on page 1, Chapter 1, an introduction. And this first paragraph that the guy writes is very important because it really, in a nutshell, says what pipe welding is all about. Only high-quality pipe welds are acceptable in modern industry. For the failure of a pipe weld not only can disrupt the operation of a plant, it can be the cause of a serious accident with the possible loss of life and property. For this reason, a pipe welder must be a thoroughly qualified person in his craft. The techniques and procedures that we teach you in the welding lab are designed to give you the knowledge and information you need to complete code quality weldments. And the limitations on discontinuities that you're held to by those codes are designed to make sure that the work you produce is safe and serviceable and there aren't any accidents or untimely failures. So as you're going through this pipe class, pay attention to the quality of your work. And don't ever lose sight that you are your own best inspector. The work you produce is a reflection on you, and the work you produce is going to affect other people for years and years to come. Let's go to your book now and read from the second paragraph. It says, the objective of this book is to describe the techniques that will result in a successful pipe weld, which must be sound throughout as well as look good. And when they say sound throughout, you've got to remember that you are joining solid steel to solid steel. And keep that in mind whenever you're making your weld. So you've got solid metal there, and when you put that weld in there, it has got to be solid metal. If you have a discontinuity, a defect in there, trapped slag, porosity, something of that nature, then you don't have solid steel to solid steel. And of course, if these trapped slag and porosity or any other indications exceed allowable limits, then you have a defect. It's very important. As a craftsperson, as the welder, the one applying that weld, you are your own best inspector. You've got to watch it. You've got to make sure that you do it correctly. To be a successful pipe welder and achieve high-quality welds, such as shown in Figure 1.1, it requires practice in welding pipe. It cannot be learned by reading a book alone. However, if incorrect techniques are repeated, practice alone will never lead to successful pipe welding. We do an awful lot of training of people who have been in industry. Some of them are quite good. Some of them, however, have never taken a lesson in their life, and they think they're doing things correctly, but they don't understand proper technique, and they don't really think about the overall quality of the weldment. So one of the tasks that my colleagues and I have when we're teaching somebody how to pipe weld is to break bad habits that people acquire over years. If you start out doing something incorrectly and nobody ever shows you the proper way to do it, you will continue to repeat those incorrect techniques, and you're not going to be successful in this as an endeavor. So pay attention to what we're teaching you and try to follow our techniques, because it's proven repeatedly through practical terms that they are successful and they are correct. Flip the page. Let's talk about pipe welding positions. We've covered this pretty much in other courses, so this is more for you those of you that have taken this as a standalone class. On page 2 it says, the welding positions are defined by standard symbols which are shown in Figure 1.2. And of course we have flat, horizontal, vertical, and then overhead where your weld is on here. So flat, horizontal, vertical, and then overhead. And they're defined as 1G, 2G, 3G, and 4G positions. 1G, 2G, 3G, and 4G. And the G, in this case, stands for groove, since we have a groove weld here. If we were doing fillet welds, instead of a G, we would have an F. So a fillet weld would be something that you might put on a T-joint. So instead of being 1G and so forth, it would be 1F, 2F, 3F, and 4F. The ones we're concerned about in pipe welding, and there's only 3 symbols used in pipe welding. We have the 2G position, like so, 2G, in which the pipe is vertically fixed. So this is called the vertically fixed position, but you're welding in the 2G or horizontal position. Then we have the 5G, position, in which position the pipe is horizontally fixed, and the weld is then vertical. And of course you can go vertical up or vertical down, depending on the type of steel, the procedure you're using, any alloying elements that's in the steel. And then finally, we have the 6G position, which is a 45-degree angle. And its nickname is an Arkansas bell hole. You may hear that term. Oops. An Arkansas bell hole. It got that nickname because in Arkansas, if you've ever been to Arkansas, you have the Ozark Mountains up in the northwest corner, and it's just hilly, very, very hilly. And anyway, that's what it's called. So you have 2G, 5G, 6G, and when you go to test out of this class that you're in, we're going to have you take one piece of pipe, this is looking at it down, and we're going to have you weld half of the pipe in the 2G position, the other half in the 5G position, and this is simply to test out of the course. When you go to do your 6G position, we will have you do an entire pipe in the 6G position. And the reason we have you do the entire pipe in the 6G is because you're not only testing out of the course with that, but if you successfully pass and you meet all the visual examinations and the destructive tests, we will write you welder certification papers based on your 6G position. So those are the positions that we're concerned about in pipe welding. Okay, going back to your book now, look down at the bottom of the page where it says, in preparing to make the weld, the welder is concerned with the following matters. 1. The type of metal to be welded. 2. The selection of the correct weld electrode. 3. The preparation and cleaning of the edge or weld joint. 4. The fit-up of the pipes to obtain the correct alignment. All of those things are important, and they are addressed in the WPS, the Welding Procedure Specification. Going to the next page, one of the things that the welder has to be cognizant of whenever they're making the weld is the puddle and the keyhole. And we're going to stress that throughout this text. When you're making this pipe weld, doesn't matter which position you're in, it's just like when we were welding plate. You want to hear that sound of penetration. You want to see that little keyhole coming across there, and you want to make sure that you're tying into both coupons equally. So you want to concentrate and focus on that keyhole as you're making your weld, particularly your root weld. Next heading is basic pipe welding procedures. It says when the pipe is in the 5G position with its axis horizontal, as shown in figure 1.3, positions on the pipe can readily be identified by their likeness to the numbers on the face of a clock. Thus, the top of the pipe is in the 12 o'clock position, the bottom of the pipe is in the 6 o'clock position. So here we have 12 o'clock, here we have 6 o'clock, here would be 9 o'clock, here would be 3 o'clock, and so forth. 2 different welding procedures are used when the pipe is in the horizontal position. downhill and uphill pipe welding. So it would be vertical up or vertical down. The choice of the method is not affected by the diameter of the pipe. It depends primarily on the wall thickness and the alloy content of the pipe. So we could be welding just a piece of 2-inch pipe, real small as this cup. We could weld 2-inch pipe in the horizontal position, but it would be vertical up or vertical down. Or we could weld a pipe as big around as this blackboard itself is. Doesn't matter. Diameter doesn't matter. Regardless of the method used, the pipes must first be tacked welded together. For downhill welding, the weld is started at the 12 o'clock position, and the weld bead is welded progressively downward around the pipe until you get to the 6 o'clock position. Then you will go back up to the top, start at the 12 o'clock position again, and weld downhill once more. So when you're welding in the downhill position, you're going to start here, weld down, start here, and weld down. Downhill pipe welding is used primarily to weld thin wall mild steel pipe having a wall thickness of 1/8 to 5/16 of an inch thick. The relatively thin wall of the pipe retains the heat longer than thick metal would. This causes the metal in the weld area to cool more slowly if the speed of welding and the heat input are the same. Slow cooling is desirable because a softer and more ductile grain structure is then obtained in the weld and in the weld area. When welding mild steel pipe, the slower cooling rate of the thin wall pipe does make it possible to deposit a weld at a faster rate without harmful effects in the welded joint. For this reason, downhill welding is preferred when welding thin wall pipe on mild steel. The ductility of the metal in the weld and in the surrounding area can be further improved by depositing several beads around the weld. Each succeeding bead heats the previous bead, which cools relatively more slowly. And a lot of these downhill pipe welders that come in here to be tested, we will time how long it takes them to make a weld, starting at the top. Maybe they'll only get a third of the way down. And we'll use our little stopwatch, and we'll time how long it's taken them to do that, and then we'll measure how far they went. By using that and the amperage off their welding machine, we can calculate how much heat they're putting into that. And we also want to check the interpass temperature. We'll take a crayon and we'll make a mark a couple of inches from the weld area to see how hot that base metal is. And all of that's designed to give us an idea of the rate of cooling in there, so that we will have some idea of what the grain structure is going to be like when they're finished. Downhill welding requires the use of fast freezing, lightly coated electrodes such as 6010, 6011, 6012, 7010, and 7014. In today's industry, in our area here in southwest Wyoming, a lot of companies are using what's called 8010. Its trade name is 70 Plus. It's produced by Lincoln, but it's an 8010 rod. It's a higher tensile strength. So control of the heat input is even more critical, because as you may recall from previous classes, the higher the strength, the more susceptible it is to cracking. So you really want to be careful about the amount of heat input that you have. As the electrode is moved down along the joint, the molten puddle and its slag covering will tend to smother the arc, causing porosity and slag inclusions in the weld. The use of the proper electrodes, proper rod angle, and adequate travel speed, keeping ahead of the molten slag, will ensure sound welds. In some instances, the use of straight polarity along with the downhill method will eliminate burn-through when poorly fitted joints are encountered. From previous lectures, you may recall that if we use a straight polarity instead of reverse polarity, we're only generating half the heat input into the weld as we would if we were using reverse polarity. Therefore, if we have really thin stuff to weld, we're going to want to use straight polarity so we have less depth of penetration. The use of heavier coated electrodes such as 7024 and the iron powder, low hydrogen type of electrodes such as 7018, they are not suited for downhill welding because of the problems of slag entrapment. They really produce a lot of slag, and they're really not designed to be welded downhill, although 7018 is in some cases welded downhill on plate. I've never seen it used to weld downhill on pipe, but sometimes it is on plate. Let's go ahead and turn the page to page 6. It says, in recent years, as the demand for larger diameter pipe with thicker walls for transporting grade oil over very long distance and natural gas at high pressure, the pipe industry has improved the mechanical properties of the pipe by additions of manganese and silicone, along with more rigidly controlled amounts of carbon. Also, small amounts of columbium and vanadium have been added, usually in the range of 0.2% to 0.26%. Such materials are known as low alloy piping because attempting to increase strength by excessive alloying causes additional problems in welding, such as cracking and embrittlement of the heat-affected zone. So we're back to high-strength, low-alloy steels here again. They're putting in just a little bit of alloying elements, and if you recall from one of our previous lectures, they can increase the strength by about 30% by just adding small amounts of these without really having to increase the carbon content overly much. Now, increasing the carbon, manganese, and silicon content to achieve these higher level mechanical properties may seem reasonable. However, it will not be in the interest of joining pipe edges by welding without risking faulty welds. Even small quantity increases in carbon can have great effects, increasing both the tensile strength and the hardness. Likewise, manganese will increase both toughness and ductility, but will suffer from not having the necessary value to resist cracking. So when you're making a weld, be aware of what that pipe, that base material, is comprised of. If it's got a lot of high carbon in it, or it's a high alloying elements in it, there are references that will tell you, and it should also explain it in the WPS that you're working from, what type of post-weld heat treatment it may need, what type of preheat it may need. It may even limit the size of the electrode that you can use. It may require that you only use a 332 electrode or an 1/8 inch electrode instead of a 532 or a 3/16, which some pipe welders are very fond of using. So be cognizant of that. Today's pipelines and all of the LX60 and LX65s grade pipe materials are being made by alloying techniques other than simply increasing the carbon and manganese levels. LX65 and LX60, those are very high strength. The 60 and 65 talks about, that refers to their yield strength. If you remember again from a previous lecture, we talked about yield strength and tensile strength. You might have API X42. That's one of the standard sizes they use. X52 is a standard size. X60, X65. These numbers refer to the base metal's yield strength, not their tensile strength. So X42 will yield, that is, it will go from plastic to elastic at 42,000. And at that point, it cannot, once you cross that threshold, by stretching it, you cannot go back to its original shape. So that's its yield point. This one has a 52,000 pound yield strength and 60,000 pound and so forth. But the tensile strengths are generally much higher. I believe the tensile strength for X42 is 60,000. The tensile strength for X60, I believe, is something in the neighborhood of 77,000 pounds. So you can see it's got a lot more strength. So you can make the assumption that it has more carbon and alloying elements in it. So therefore, it's more susceptible to cracking. When you qualify a welding procedure to API standards, if a change in metal group, and API divvies these up into different groups, would require a different procedure. If I made a weld using X42 pipe with 6010 and 8010, that procedure would not be qualified to use on X65 because it's such a much higher strength steel. We would have to qualify an entirely new procedure. You have to take precautions. Here, if you're welding X42 or X52, we may just take a rosebud or a cutting torch and drive the moisture out of the weld, and then we'll go ahead and put our weld in and be done with it. Here, because we have a lot stronger, higher tensile strengths, we're going to preheat that up to 200 degrees. We're going to take special care to make sure it's preheated to 200 degrees. Then we're going to produce our weld, and then we may want to wrap the weld when we're done. Wrap it with some asbestos blanking or something in order to let that heat precipitate out of there more slowly and relieve some of that stressing. So pay attention to the amount of carbon, the type of material that you're welding. Again, it goes back to you as the welder. Don't trust what anybody else says. If you have an opportunity, read the welding procedure and know. Okay. Again, we're still reading from page 6. It says, pipeline welders are on the go all day. They are provided with welder helpers who are responsible for grinding and wire brushing each layer of weld deposit. They are also responsible for adjusting the welding current as instructed by the welders, keeping the welder supplied with electrodes, and handing the welders an electrode each time the one in use is consumed. The welders' helpers play a very important role because of their knowledge and experience in grinding and brushing weld complements the welder's efforts in making perfect welds. So if you ever run your own truck and you have a welder's helper, you want to be sure that that welder's helper is competent in his tasks, because if he messes up, it's going to be a reflection on you. Going to the next page, it says, because of their role with preheating, interpass temperatures, screening welds from wind and rain, and observing surface defect, welders' helpers should be formally trained. And says that, note, Chapter 8 continues the discussion on pipeline welding. So if you have a welder's helper, make sure that he knows what he's doing. Uphill pipe welding. After the pipe has been tack welded, the weld is started at the lowest spot on the pipe or at the 6 o'clock position. The bead is deposited upward around the pipe until the 12 o'clock position is reached. So out in the field, if you're going to weld in the vertical up, and this has to be written on the paper, by the way. Vertical up. This is called your progression, or vertical down. And it would say the papers would say 5G, and then either vertical up or vertical down. Out in the field, you're going to start down here at the 6 o'clock position and weld up. 6 o'clock position and weld up. But I always recommend to our students, and this is an important thing, to stagger your starts and stops. If you put your root pass in like this, when you start your filler, come over across bottom dead center a little bit and weld vertical up across bottom dead center a little bit, and then complete that weld on the other side. Then with your next bead, come over here across bottom dead center a little bit and come up across top dead center, and then complete that weld. So you're staggering your starts and stops. There's a couple of reasons for this. By staggering your starts and stops, you're going to get a little stronger weld in here. But more importantly, if your work is going to be X-rayed, there are limitations to the amount of defects that you can have in any single square inch of your weld. So by staggering your starts and stops, if you've got a little bit of porosity here and maybe a little slag right there and some more porosity there, you've spread those defects out over a longer area. When that X-ray technician shoots that, he can see, well, here's porosity, here's slag, here's porosity, but he'll compare it to the code that you're working to, and he'll say, okay, this is okay, it meets code requirements because it's spread over this long of an area. But if you make all these starts and stops here in the same place, gosh, look at this. Now you've got such a concentration of defects that exceeds allowable limits. That's a rejection. So you want to make sure you stagger your starts and stops, and even coming up the side. Don't stop at the same place every time. Take them a little bit further, and then back them up. So you want to have at least a half an inch between each start and stop. Preferably more like an inch between each start and stop. Okay, going back to your book again. Page 7, the paragraph just above that photo, it says, this method is preferred for welding heavy wall pipe and pipe made of alloy steel. The thicker pipe wall acts as a heat sink by withdrawing the heat more rapidly from the weld area than does a thin wall pipe. The faster cooling rate causes the metal in the weld area to become more brittle in mild steel pipe. In alloy steel pipe, the tendency towards brittleness is greatly increased. To overcome this tendency, the cooling rate in the weld area must be reduced. This can be accomplished by decreasing the welding speed and by depositing a heavier bead. Both of these objectives, slower welding speed and a heavier bead, are achieved by welding the pipe in the uphill position. So since we've got thicker pipe, we want to heat it up a little bit more. So welding uphill, that's slower than welding downhill, but it also allows you to deposit a larger weld bead. And another thing you can do, depending on how heavy the pipe is, of course, you can preheat it. And I would always recommend preheating, regardless of what you're welding. If to do nothing else than to just simply drive the moisture away from the weld joint. Moisture, of course, contains hydrogen. Hydrogen can get into the weld puddle, causing porosity or even underbead cracking. So I would always recommend that whatever you're welding, grab a torch and drive that moisture out of there. Horizontal pipe welding. When the pipe is in the 2G position with the axis vertical, remember we talked about vertical fixed. This is the horizontal. Here's your weld. The weld joint connecting the two pipes is in a horizontal plane, and a horizontal plane or 2G weld must be made around the pipe. Horizontal pipe welding will be treated in detail in a later chapter. Basically, let me say real quickly that everything you do in the horizontal position's got to be stringer beads. Every pass is a stringer bead. Don't ever try to weave in the horizontal position. Going over to the next page, last page, it says, since public health and safety are involved in almost all of these cases, codes and standards have been established to protect the public interest. The following organizations are primarily responsible for these codes: the American National Standards Institute, the American Welding Society, the American Society of Mechanical Engineers, and the American Petroleum Institute. And that's pretty much the high points of this chapter, and I have mentioned in this little review, I've touched on every question that will be on your test. So go back over, read it, study it. If you have any questions, get with Jeff and I, and we'll go over it with you a little more thoroughly. Thank you.